In computer graphics, let us talk about 3D viewing now. This is 3D rendering pipeline, and thus we see this is a pipeline sequence of operations to draw a 3D primitive into a 2D image for direct illumination, which gives it a 3D effect. So these are our 3D primitives. We know by now what are 3D primitives. So first we perform the model transformation. Then lighting is done. Then we perform the transformation for viewing, then the projection transformation, clipping, and then viewport transformation, and then scan conversion to the image. So this is the 3D rendering pipeline sequence. So in the first step, when 3D primitives is input, the model is transformation is done. That means we transform now 3D primitives into 3D world coordinate system. 3D world coordinate system. Then in lighting, we illustrate according to lighting and the reflectance, because in lighting a source is kept, what lighting is there, and with respect to the lighting the shadows are also being shown. Now after this viewing transformation is done, that means we now transform the 3D world coordinate systems that we did in model transformation to the 3D viewing coordinates system. After this, we do the projection transformation. Now, because this is 3D and projection, we know that transformation from 3D to 2D is the transformation. So, we transform this 3D viewing coordinate into our 2D viewing coordinate. Then comes the clipping. Clipping means we clip primitive outside Windows view. So, if this is a window, all those things which are here, we clip them. And then we perform the viewport transformation. That is, we transform it to the viewport to actual showing. Viewport is where that port where viewing or show or display is to be performed. Then the scan conversion, that means we draw pixels, which includes the texturing, the hidden surfaces, etc. So the scan conversion is done so that the image can be shown. So these are the transformation: model transformation, viewing transformation, projection transformation, and viewport transformation. These are different transformation that we apply right from the 3D primitive to the image conversion. So what is this transformation? Now we have some points, say x, y, z, right? We have 3 points, x, y, z. Then this is the 3D object. In this it is in 3D object coordinate, you can say. So we perform the model transformation to make this 3D, because this is an object only. So we convert this 3D object coordinate, certain model transformation is done to place it at the 3D world coordinate. That means now this is 3D object coordinate, say x, y, and z point. Every point has some x, y, z value. And now this 3D object coordinate is converted into the 3D world coordinate. Now this is the 3D world coordinate, right? After this 3D world coordinate, then we apply the viewing transformation, which converted to 3D viewing coordinate. Now this is converted into this, and this is converted into this 3D viewing coordinate. So this is x, y, z corresponding to this 3D view. And then the projection is transformed so that it can be placed on a 2D projection coordinate, and then the viewport transformation, that is it is shown on a 2D device coordinate, because this is 3D, you have to show it to the 2D device coordinate. So for that you need certain transformation. So x, y, z ultimately changes into x dash, y dash. In this transformation, these two, means 3D world coordinate to 3D viewing coordinate, these are the viewing transformation. These are the viewing transformation or project transformation. Okay, so what is this viewing transformation? As we have just talked about the various serial or sequence of steps which are taken. So what is viewing transformation? What happens here? We are mapping from world to the viewing coordinate. We are trying to map, because what is there is in world coordinate. Now we want to show it onward your system or display. So first you have to convert it to some viewing coordinate, some x, y, z coordinate. So the origin moves to the I position. This is the origin. This is the I position, or it can be anywhere. It can be represented by like this. I. So I position, origin moves to the I position, and up vector. This up vector maps to the y axis. The right vector, this right vector, this maps to the x axis. So this maps to x axis, this to y axis. Now the coordinate, the origin moves to the I position. So this is the I position. and this is the camera position. So this is I position, Y, X, and of course the distance, the perception of distance is represented by Z. This is the transformation from the world coordinate to the viewing coordinate. So what are the sequence of transformation which just takes place? So this is the general sequence which I'm going to tell you about the translate or rotate transformation, translate or rotate transformation. So these are the transformation sequences, translate and rotate transformation. So what happens here? We translate the view reference point to the origin of the world coordinate system. So what we have done, this is X, Y, and Z. Now we took it to our YW, XW, ZW. So this world coordinate, these are the world coordinates. Now we want to convert from world coordinate to the viewing coordinate. So we translate the view reference point to the origin of world coordinate system, this to this. Okay, then we apply the rotation. This is the transformation sequence of translate and rotate I'm telling you. So this is taken here, and now the rotation is performed here. This is rotation. This comes to this, XV come to Z, this point, okay, ZV point, and YV goes to this point, YW, and XV, this takes the XW point. So this is how it is rotated. So we apply rotation to align this XV, YV, ZV to the actual world axis. So this is how we do the translation and rotation transformation. So the transformation from WC to VC, that is world to view coordinate, in this translation is performed, and this can be easily represented by, you know, what this matrix is. We have discussed it already in the previous section. This is the view reference point, say X0, Y0, Z0. Now using this you can transform T, multiply this T, or use this matrix X0, Y0, Z0. So you can translate view reference point like this. Okay, this is the basis matrix that we have seen. And what about the rotation? Translation is done by this. What about the rotation? We rotate around the world XW axis to bring ZW to XW, ZW, and likewise we rotate YW to along ZW and ZV axis, and the final rotation is about ZW axis to align it to YW and YV. So this is the rotation by UVN system. What is this UVN? We calculate unit UVN vectors, that is U is perpendicular to both N and V. What is N? This is the view plane normal vector, and V is the view up vector. So this is the N, that is capital N by the magnitude of N, which is given by N1, N2, N3. U is given by U1, U2, U3, which is nothing but the view up vector into the view plane normal vector divided by the multiplication and then the magnitude. And what is V? V is given by simple N into U, that is V1, V2, V3. So now we have the composite rotation matrix using these three. So we can just use them and apply the composition rotation matrix like this. So now the M could be, that is WC to VC, can easily be this R into T. R you have already seen. This is R, and what was the translation? This is the translation. So we apply R into T, this into the previous one, and you can transform from the world coordinate to the view coordinate. So these are the various camera models. The most common model is a pinhole camera model. So this is the eye position, pinhole. This is a view plane. This is how you see a 3D object in a view plane. So the most common model, as I said, it is a pinhole camera, and all captured light rays, they are arrived along the path towards the focal point without any lens distortion. Everything is in focus. So the sensor response is proportional to the radiance what is coming from here. Okay, so there are other model also we can consider, like depth of field and motion blur, lens distortion can be there. These are the viewing parameters. First is your position, that is your eye position. This is your eye position, that is Px, Py, Pz, given by Px, Py is Pz. Then we have orientation, that is the view direction and up direction, and this is the eye position. Then the aperture, that is the field of view, X FOV and Y FOV, Y field of view. And then film plane. This film plane is look at point and view plane normal. Okay, this is these are the look at point. These are the look at point, and these are the various eye position. As I said, eye position Px, Py, Pz. This is the view plane. Okay, So viewing coordinate, we can have a canonical coordinate system. The convention is always right-handed, looking down minus z-axis. Looking down is our z-axis, that is looking down z-axis. The convention for projection, clipping, etc. can be taken in canonical coordinate system. So if this is a coordinate system, this is x, this is y. So this y is the viewing up vector maps, which is mapping to the y-axis, viewing up. Viewing right vector maps to the x-axis, and now the z-axis. Viewing back vector. This maps to the z-axis. That is the plotting out of the edge. This one. Okay. So now this viewing transformation, the transformation matrix maps the camera basis vectors to the canonical vectors in the viewing coordinate system. So we have seen what is up, where is the eye, where is the back, where is the right. Now we can convert it into certain matrix. Now we can get the values like this. So after this viewing transformation, now we come to the projection transformation. These are the projection transformation from 3D viewing coordinate. Now we have converted world coordinate to the viewing coordinate. Now we want to come to the 2D projection coordinate. So what is the projection? Projection is 3D to 2D in simple terms. So general definition is the transformation of points from n space to n space. Means n space to m space, that is n is greater than m. N space to m space. So n is greater than m. That is 3 is greater than 2. So in computer graphics, map viewing coordinates, we convert into 2D screen coordinates. So these are the projectors. This is the center of the projection, and this is the projection. So this is the taxonomy of our projection. Planar geometric projection can be parallel and can be perspective. The two type projection are possible, parallel and projective. And then in parallel we can have orthographic projection and oblique projection. So in perspective we can have 1 point, 2 point, 3 point. In again orthographic you can have top, front, side, and axonometric. In oblique you can have cabinet, cavalier, and others. So this is the parallel projection. This is the line which is shown like this, parallel projection. This is the perspective projection. What is the perspective projection? This is the projection reference point. So these points, they come down to a central position, and where they hit this plane, this is our perspective projection. Now we come to the parallel projection. What is the parallel projection? The center of projection is at the infinity. In the parallel projection, all these rays are parallelly, you can say, they create an impression on the view plane, and this is the direction of projection, which is same for the all points, because the center of projection is nowhere, so they are not going to, of course they are going to meet at some certain point at infinity, but right now here they are not meeting. They are meeting this plane and creating an impression. This is the parallel projection. So parallel projection can be of orthographic and oblique type. So this is the parallel projection view volume. See, this is the simple projection, how you can present it. This one in the form of window, and these are the orthographic and oblique projection. This is orthographic, and if certain angle is used, then this is the oblique parallel projection. So orthographic projection is like this, or oblique projection is with some angles. Orthographic parallel projection, the projection is perpendicular to the view plane. Okay, it is perpendicular to the view plane like this. And oblique parallel projection is the projectors, these are inclined with certain angle, this angle with respect to the view plane. Okay, and in this orthographic projection, we can have front. If you see from here, front. If you see from the top. If you see from the side, to this side. So the direction of projection, which is perpendicular always to the view plane, these are the orthographic projections. Front, top, and side. Then these are the orthographic coordinates. Once we have done the projections, these are the orthographic. This is now your plane. So x v, y v, z v. So if this is x, this was x y z, this has come down to x y now. So what is this x? This is axis xp, that is on the projected plane, and y is on the projected plane, yp. In the case of oblique projections, this DOP is not perpendicular to view plane. So you will get a DOP, that is direction of projection, to say some 45 degree. This will be seen. If the angle becomes 63.4 degree, the projection will change of the same object. So if we apply to the oblique projection, if DOP is not perpendicular to view plane, of course you'll get 45 degree here and say 30 degree here. And in the cabinet projection, again, if tan alpha equal to 2 and alpha is 63.4 degree, say these are the views. Then we come to the parallel projection matrix. So this is the general parallel projection transformation. Xp can be given by x plus L cos phi. Yp is given by y plus L sin phi. So this is xp, this is yp. So xp is given by what? X. This x plus L cos phi. Okay, and yp is given by y plus L. This is cos, this is sin. So sin phi. And of course, you can find out the tan alpha. This is the alpha. You can find this is the x y z point. This is the projected point, and these are the point which is perpendicular. So now with these 3 points, you can compute this alpha and xp and yp, of course, with respect to the alpha. And also you have various values given here z. So where this L1 is what? It is the inverse of L1. We have taken as the inverse of tan alpha, which is also the value of L when the z is equal to 1. This is the general parallel projection transformation. So now what we have just seen, these can be represented in the form of our matrix. So now xp, yp, zp, wp, all these points can be computed from x, y, z using this relationship or this matrix. This is a general parallel projection transformation. So in terms of parallel projection matrix, this M parallel projection matrix can be easily given by, because this is the original coordinate description of object. Now this is the projection on the viewing plane. And now this can be given by this matrix. So now we come to the perspective projection. Perspective. So in this perspective projection, this is how what we see. So map points onto viewing plane, this view plane, along the projectors. These are the projectors emanating from the center of projection, from here. Okay. So these are the perspective projection views. See, these are 3 perspective points. This one, this one, this one. So, and these are with 2 perspective points. These are with 1 perspective points. So perspective projection has view volume. Here you can see a frustum. So in this is the back plane, this is the front plane, and this is the view plane. This is the black plane, this is the back plane, this is the front plane, and this is the view volume frustum. Frustum is a part of a pyramid. So this is the projection reference point, and this is the window. So this is actually our window where we are going to see. So in the perspective projection, we compute 2D coordinate from 3D coordinate with respect to these similar triangles. We use these similar triangles because we have this frustum, as you have seen. So this is x, y, z, and this is the view plane, and this is the distance d from the origin 0, 0, 0, and this is the negative z direction on the away from the user. So what are the coordinates of the points resulting from this x, y, z onto the view plane? This is equal to x d by z, y d by z. We have used simple similar triangles relationship. So the perspective projection matrix, this is a 4 by 4 matrix representation. So let me tell you that first xp and yp we have already computed to be xd by z, yd by z, zp is d, yp is 1, x dash equal to x, y dash equal to y, z dash equal to z, wp is given by z by d. So xp, yp, zp, wp can be given easily by these transformations. So ultimately this will be the matrix for perspective projection transformation. This is the perspective projection, this is the orthographic projection, this is the again perspective projection. So this is the center of projection on the x-axis. This is the, if we take the center of projection on the y-axis. So this is the M for the perspective projection. This is 1 by dx here, 1 by dy by here, because the COP is now on the here the x-axis, here the y-axis. Now these are the 2-point perspectives. You can take any of these. This is the 3-point perspective. This is 1 point. You are viewing from 1 point. This is from here. You are viewing from 2 points. Here you are viewing from 3 points. 1, 2, 3. So how this can be seen? You see, this is proper. There are variations of proper. Now you can see actual 3D here. Though it is not 3D, represented on a 2D plane only. Then what about the differences or discussion on perspective versus parallel? Perspective projection, the positives are size varies inversely with distance, so it looks realistic. A parallel projection, it is good for exact measurements and parallel lines remains parallel. What are the negatives of perspective projection? Distance and angles, they are not preserved, and parallel lines do not remain parallel. In the parallel projection, what are the negatives? Angles are not preserved and it looks less realistic. This is the classical viewing. Front elevation, elevation oblique, plan oblique, isometric, 1-point perspective, 3-point perspective. So this is the discussion about 3D viewing. I hope you'll go back to your book and learn each and every aspect of it. This is just an overview. Thank you so much. Take care.